Welcome back. I'm a little more caffeinated than I was before. I don't know, just trying to keep it easy. In the next bio, there's a reference to coffee. I really appreciate it. Micah, are you out there? And are you Micah'd? Micah with the Micah. I'm just so funny. Micah Bhakti, he works for Intel. He works in the high-performance data division. He focuses on product management, software partnerships. He's been at Intel for 5 years, previously worked on private and public cloud computing before moving to Lustre. His current projects include running Lustre in the cloud, Hadoop on Lustre, and cache hinting. In his free time, he drinks copious amounts of coffee. I feel a deep affinity with you. Ladies and gentlemen, Micah Bhakti.
Okay, perfect. Just forward and back. Thank you. Can you guys hear me all right? I just got an espresso machine for home. It's bad news. Okay, so today I'm going to be talking about intelligent cache hinting. You'll notice as we go through the talk that I'm not going to spend very much time talking about the back-end cache. It'll be mostly focused on actively passing hints. And the reason for that is we've used a specific software cache for the work that we've done here. But our intention is that you'd be able to do this with any kind of hardware or software back-end cache that you want for this. So we won't focus too much on that. We'll focus more on kind of how we get there. And the way we'll run through it is we'll talk a little bit about some of the problems that we've faced, and then we'll talk at a high level about the methodology that we're planning to use, and then we can talk about the actual execution and implementation with Lustre and how that integrates, and then we'll look at a little bit of test configuration and some benchmark results, and run through those and talk about what those mean. And if you're paying attention to the slides, there's a little bit of a spoiler up there, but we'll talk about that more later. So. First, why do this? Why do anything? There's a couple problems that we've noticed talking to some of our customers when we're working with Lustre. There's some things that Lustre does really well, sequential I/O, and there's some things that Lustre doesn't do quite as well with, so small file and random and things like that. And so some of the customers that we've talked to will use Lustre for large sequential, and then they'll end up using other file systems or other storage to do some of the more small random I/O. And so they might deploy a filer or something like that to handle those kinds of workloads. So that creates some difficulty managing multiple systems, and it's just not quite as ideal as being able to run different kinds of varied workloads all on one storage system. And then the other thing is, it would be great to run everything pure SSD, and I think as Intel, we'd love it if everybody wanted to buy our SSDs and put them in everything, but that's not maybe realistic, and the cost right now is prohibitive, as well as there's some other things that that SSDs maybe don't do as well with. So it's not always the best thing. So we'll talk about that a little bit, and then there's also some issues with traditional caching and the way that it's done. So. When you look at traditional caching, they're inefficient at keeping the right data warm in the cache, especially when the cache is cold. And application context can be lost when you're passing data to the storage system. So what I mean by that is, as you're passing metadata or you're passing small or large files, the context of what's important within that data is not always apparent. So we want to kind of focus on that. And then also end-to-end quality of service and looking at what kind of I/O and what kind of storage is being called to the file system and how that's being managed, especially when you have different applications that are writing significantly different types of I/O workloads. So if we look at this conceptually, the way that we kind of think about it is we've got classification, we've got policy assignment, and we've got policy enforcement. And so the analogy that I like to use for that is shipping moving boxes from one house to another. So say you're moving across the country and you want to box up all your things. You might box up dishes from the kitchen, bedroom stuff, some toiletries from the bathroom, and then you want to relocate those to your new house. And so for those different types of packages, you'll have different policies. So your dishes might be fragile. You might want your toiletries and your clothes to arrive first, so you have access to those. So there's going to be different policies for different types of data that you're shipping. And then ultimately, you want policy enforcement. So you want your moving guys to not be throwing your fragile stuff. You don't want your bathroom toiletries to end up in your garage, things like that. And so as we look at the storage system, we kind of do the same thing. We look at application data, and then assigning storage policies to that, and then ultimately wanting Lustre to enforce those policies that we've enacted. So looking at how we would do that, we've got the same kind of 3 stages. If we look at classification, the way that we've implemented it here in our kind of test is to send classifications from the file system. We could do that also from the operating system or from the application, and we'll talk about that a little bit. But right now for this, we've done it directly from the file system itself. And then we'll assign policies to that. So we create a range of policies, and then we can tag things like metadata, small files, large files, different size ranges, and we can create a group number and assign that group number to those types of data. And then on policy enforcement, we've got our storage controller underneath interpreting those group numbers, and then assigning priorities to those group numbers, and then storing it to different storage pools depending on the priority that's been assigned in the controller. And so the way that we pass those policies is through the SCSI CDB. So if we look at that, we've got over on the left here, if you see byte 6, we've got an area in there called group number. And so essentially what we've done is we take 5 bits in the group number, which gives us up to 32 classes, and we pass that through in the SCSI CDB so that we can allocate different groups to the different types of data. The other component of this that we need is the cache implementation. So I talked about we can use different caches. We're not tied to a specific cache, but there's some things that you need to do in whatever cache you use to make it operate correctly with the hinting. So we've got, the first thing is selective allocation, which essentially means we've created bucketed LRUs. So rather than using one large LRU, we create tiers, and then each one gets assigned a priority. So we have I/O assigned to different LRUs based on the class that we've assigned to them, and then they're fenced off from each other. And then the other thing that we need is selective eviction. So we want to be able to push things out of the cache depending on their priority, or hold things in the cache indefinitely, even if there's pressure on the cache. So we can soft pen or hard pen depending on how we want to structure those policies for maintaining data within the different buckets of LRU. So we then kind of looked at how we would implement this in Lustre. And for this test, I think there's a number of different ways that you could do this depending on your needs. But for our needs, we started looking at client-side caching. And for us, it was a little bit tricky, just because normally we want to be able to run a lot of clients, but we don't necessarily want to purchase SSDs and allocate them to each and every client. Especially when you're borrowing hardware to do tests and things like that, you maybe want to try to get by with as little as you can. And then there's an overall cost component. And then there's also cache coherency issues. So if you have multiple clients that want to read and write from the same cache, you have issues if it's local in the clients and figuring out how to manage those issues. And then there's also, if we drain cache from the clients back down to the file system, then that can cause QoS issues depending on how that's implemented. So for our testing purposes, it was preferable for us to do it on the server. Fewer devices, it's a little bit easier for us to implement, and it ends up being transparent to Lustre if we do it in the OST. So it can fail over with the OSTs, and it just kind of runs underneath what Lustre's doing. So if we look at the changes that we made to Lustre, we've got a couple of LDiskFS and kernel changes. We're adding classifiers to the I/O requests in the SCSI CDB. We have it set to only coalesced like types. So essentially, if we have different group numbers and we package those together and then send them down to the storage system, they're not going to be able to go into their respective buckets in the LRU. So we're only doing like types. And then we've identified 18 types for this. You could do 4 types, you could do 18, you could do 32, but for our purposes and the workload that we were looking at, small files and metadata, we did 18 types. And these changes are a one-time change to the file system. And the interesting thing too about, if we look here at the group numbers, We've got individual group numbers for each type of metadata and then some of the different file sizes, but the cache priorities can be the same for multiple types. So you see here that all the metadata items are high priority as 0, and then we've got some other priorities kind of staggering for other types of data. And when we are assigning these in the SCSI CDB, if we're passing these through and it's going to a storage system that doesn't have a cache device that's set up to recognize these hints, the data will all just flow through. So if it's not looking for this, then it's not going to have any kind of downside or impediment to the storage system. It's just not going to be able to allocate to different buckets in LRU. So for our performance analysis, what we wanted to do is we wanted to look at the use case that the customers had talked about that we were working with. And so we took traditional Lustre I/O using IOR, and we combined that with small file and random I/O using Postmark. And so we wanted to run those to kind of assess how that workload would do on a hinted environment. We used 10% cache for that test, and we wanted to see, is that enough? Do we need to use 50%? Do we need to use 80%? And then we also wanted to compare this bucketed LRU methodology to just a traditional LRU and see how performance would compare there. And the performance gap to pure SSD. So if cost wasn't an issue and we just wanted to throw a bunch of SSDs in there, what's the difference between 10% SSD and full SSD? So looking at our test cluster configuration, we've got 2 socket Xeon servers that we're running, 10 gig Ethernet, 10 terabytes of storage, and we have a pretty basic setup. We're just doing 2 clients, a management and metadata server, and then 2 OSSs. And we did our testing using 1 OST and 2 OSTs, and there wasn't a significant difference between those. Both configurations are consistent with our results. So here's a diagram showing the benchmark configuration. We've got the 2 clients there. We've got the Postmark client, which is running a SpecFS-based file server kind of configuration workload. So we've got 300,000 files from 1K to 32 megs, 10,000 subdirectories, 30,000 transactions. And then we're simultaneously running IOR on the other client. And so that IOR is doing a loop of a 20 gigabyte checkpoint file, and then we've got some data sets in there. And so those are running concurrently to simulate multiple clients with significantly different workloads on the same storage system to see how hinting can impact that. So looking at the results here, I'll kind of walk through this because there's a lot on this chart. But if we look at the diagram on the left, we've got pure hard drive. And then stepping through the lighter blue, we go from metadata and then add metadata plus 4K. And then we kind of add the amount of data that's getting cached with our profiles all the way up to caching everything. And then we have LRU, and then we have pure SSD. So there's a couple interesting things. One, just looking at it, we can see LRU performs worse than hard drive, actually. And that's because of the multiple workloads and things getting pushed out of cache, and then we've got misses in the cache. And so for this specific workload, LRU is actually a negative impact on performance. And we can also see if we're just caching metadata, we don't have a huge improvement here, so we're not getting a lot of value out of that. But if we look through, it looks like I think the optimal is metadata plus everything through 1 meg. We kind of have a path to not only see here what was the most beneficial, but also look at different workloads and analyze, depending on what my workload is and what my clients are doing on the file system, where's the sweet spot for me to cache? And so because the data that's getting passed through the file system is just group numbers, and the profiles are done in the cache itself, you can actually change that depending on what your workloads are to be specific to the optimized performance for the types of things that you're running. So that was kind of interesting, and finding that sweet spot between caching too little and caching too much. So ultimately, we got 3.9% performance improvement on this set of tests when using 10% cache versus just hard drive. And the other interesting thing was that the optimal performance is about 85% of pure SSD. And the pure SSD configuration that we were using, we stored about 20% of the data to fill up that overall SSD. So we've got a condition where we've got an unused virgin SSDs using a small portion of the storage, and we're still able to achieve about 85% of the performance, which is 10% SSD. So that's optimal SSD performance on the pure, and with the cache hinting, it's really not that much difference. So there's a couple things that we want to think about doing next, potential future improvements. One is standardization. We'd like everybody to use this. We're working on this in the context of Lustre, but I think this is valuable beyond that. There's things that could be done with other file systems, virtualized, non-virtualized, things like that. And so what we'd like to do is we're engaged with the T10 organization to try to create a standard set of classes for the SCSI CDB that would define different data types. So what we do with that is we basically provide a reference schema that developers could use when they're implementing their cache devices or creating storage platforms, and they'd be able to use that. We don't want to make that a de facto standard that you have to use. We're just setting this forward as something that we've decided to use, and if others want to use it, they can use that too, or they could implement another standard with fewer or more group types. And then also, we've been working with Intel Labs on this, and Intel Labs is working to upstream these kernel patches into the Linux kernel. So this is something that we want to see everybody be able to play with and figure out how to drive it forward and take advantage of it. So that's really exciting for us. The other thing is hinting. Right now, we're doing from the file system in this test, but there's a great opportunity to do it from the user level too, and do applications that are sending their own hints. So if applications are sending these hints, they can define what types of data are important to them. If they're not doing that classification, you can still have the file system adding those hints. So you're not losing anything by doing that, but you get a little bit more control and granularity with optimizing for specific applications. The difficulty that we've had so far is just a lot of the applications are either proprietary or hard to get a hold of and figure out what they want to do and how we could work together on this kind of thing. So my reach out to you guys is if you have applications that you're interested in kind of talking about cache hinting with them or want to reach out to labs or to our team and talk about what kind of things we could do together to try to implement some hints in your application and work together on that. I'd love to hear suggestions or ideas or thoughts on that, kind of integrating those together. Last thing, I just want to say a special thanks to a few people that were instrumental in kind of bringing this to us and implementing the tests that we have here. Michael Manier and John Keys from Intel Labs. Thank you guys, I really appreciate it. And then Andreas and Hongchao Chang, both on the Intel side, for getting this all set up and allowing us to do this. And then we also have a little bit of information here. If you're interested in kind of the Intel Lab side and some of the work that they're doing on hinting and what kinds of other applications there are for it, we've got some links to read up a little bit more, or you can come talk to us. John Keys is here. And I'm here, obviously, so if you guys want to meet up afterwards, too, we'd love to kind of talk and answer questions or just get thoughts on how this could be used. That's it. Questions?
So it appears that you are on track to significantly, I may say dramatically, improve the performance also for tons of really small files with this mechanism, because there's still those arguments floating around, and of course told by non-Lustre vendors that Lustre is pretty bad in environments where you have hundreds, thousands of small files where there's a smaller number of very, very large files. Right. Is there any quantitative data you can provide, or you will be able, comparing it to other file systems that are known for being good in handling, huge amount of small files?
Yeah, we haven't done a lot of that yet, but running the Postmark benchmark was kind of targeting some of those workloads that those other systems do well with. We'd love to run kind of against some other solutions. It's also worth noting this isn't, it's not a silver bullet. It's not going to fix everything. There's still, issues with multiple RPCs. There's other ways to go about this. You can do pools of SSDs. You can do data on metadata. There's other things too, but we think that this is kind of an interesting part of that. And if we can achieve the benefit that it looks like, we're able to get it's something to kind of figure out how we can move it forward, and if application hinting provides a big benefit, and there's also an opportunity to use the hinting to look at what the data is doing within the file system and have a little bit more visibility of what's going on, and then be able to tune based on that visibility. So there's both the performance aspect and then also the kind of the information coming out of it.
So in the administrative interface for this, right? So we've talked about from the application, but so say we wanted to identify a class of files, or based on some criteria like their age or who the user was, then is there a way to attach that class to these files once they were recalled or accessed, or something on the lines maybe of madvise, but a static configuration that allowed you to do mapping on the servers itself without the application having to go to that level of detail?
Yeah, so there's some different stuff that we could do. There's not a GUI user interface for configuring this stuff right now, but there's a potential to do tuning on the cache devices, so we could change the priority of different items on the cache devices. So because the group numbers are kind of static and then the priorities are all dynamic, you could define those. Right now we have it set up so you'd have to define them based on data sizes or metadata types or things like that. But if you had an application that you were running and you knew that a certain size file or a certain type of metadata was really important, then you could classify that and tune your profile depending on what you want it to do.
Right. So it's more that you want to identify, select a group. So you've got 10 million files out there, right? And so as an administrator, you might want to say, okay, this guy's work is important, and so it's either UID or maybe it's his work is important for the things that he's done in the last 30 days, or we know that this particular class for his is, lots of small files, or, so from the users often, we can contact, individuals and maybe get them to do things, but in general, they're busy doing other things, and so they might even not actually have control over their I/O subsystems. They may be developed by other people, and so there's really sort of an administrator side to this of how to interface with the caching in a way that's beyond simple block sizes or the type of data or the age, just things like that.
Well, and not just the application, but looking users in the application and which users you want to grant different priorities within that application. So I don't have an answer on how to do that, but we'd love to talk about what we might do to kind of further that, because it would be a great thing to be able to add.
I have a couple of questions. The first one is about the size of the cache. You said that you tested with the 10% the data in the cache. Yeah. I mean, and you got with this figure, you got almost 4 times improvement. I mean, did you try from say from 0 to 1 the cache size to see, and that was the optimum for this kind of workload, or?
Right. Because as we see, when we get to the 100% SSD, there's a negligible difference between 10% and 100%. So that would change depending on your overall storage size, how large your files are, what you're saving in the file system, and how much you want to take advantage of that cache before it fills up. So that's going to be kind of a dynamic thing. But 10% was basically the lowest amount that we were able to use to get incredibly significant performance improvement, but that's something that could be tuned or changed depending on the specific configuration.
The second question is about application. You said that you are also asking about application from the user perspective, and in my shop we do have an application that really suffer from small files cars. And one of the most important application is the backup, because when we have to run full backup, and I'm talking about a file system that is composed by 20 million a little bit less than 20 million files, each one of a median size of say 4 kilobytes. And I wonder whether we can try to apply some of these techniques for this, for the backup application, full backup application.
Yeah, it would be interesting to look at the application and see, what the file usage is, and if that's something that that would benefit from this. We're kind of always interested in different workloads and things that we could run either on our test cluster or assist other people with kind of setting up and testing out. So if that's something that you'd like to work on and actually, we could speculate or we could, try to run it and actually figure out what it looks like and do that. That would be something that we would be really excited to
But
kind of
this is possible to run also with the Lustre 2.5.
Yeah, so the test configuration that we have on here is 2.5. It's running on CentOS 6.4, I think, but 2.5 is what we ran these tests with. Yeah. Yeah.
So right now the group number, it appears that it's going in the direction of a hard-coded enumerated list. And listening to the audience here in the previous talk, it sounds like it might be far more flexible if that were an index into a site-specific table of properties and attributes. How difficult would it be to adapt these enabling technologies to do something like a site-specific indexed group number and the behaviors that go with it?
Yeah, that's something that we haven't looked at yet, and in our tests we're only using I think 18 of the classifications out of the 32 that we could get from the 5 bits that we're using in the CDB. We could talk technically and figure out if there's stuff that we could do, but I think at least in our kind of early work with it, a lot of the benefit comes out of just kind of identifying certain groups and that for our tests. Having 1,000 different classifications wasn't necessarily beneficial to us. But if there's certain workloads or things that you're doing where you think you might want more of those, we could talk about ways to kind of make that less hard to find and figure out if we can do that.
Yeah, I could see something like this being used even in terms of security context and things outside of performance enhancements. And so being able to do arbitrary tagging of read and write data paths, even from an academic studying the way the data is distributed, it could come in very handy. And again, that's all site defined and implemented.
Yeah, that's a really interesting idea.
I have one more quick question. The power commits handler, are they right through the back end, or do you stop?
So we're doing right through right now.
Okay.
Is how we're handling that. Yeah, and that would be dependent on the cache implementation. The software cache that we're using with failover, we do right through so that we don't lose any data if there's a a hard failure of the.
So what if you were okay with the SSD being right through enough, though, right? So it's written through a lot to actually get to that point, and it's static storage to, so it might be good enough. And so what we see, of course, is that whenever you do, there's, this thing, the commit process for various things, whether it's, deleting lots of files or updating metadata within, the OST file systems, that those actually are pretty disruptive. And so a lot of times they're seek limited. Especially if they're interleaved with lots of random activity that's going on. So that commit operation, making that a little bit loose but safe, right? And so is it safe in an SSD? We'd have to have experience, right? Because these things, of course, can catastrophically fail. Their failure modes are different than disk drives, and so that's something that I don't think is really well understood. But being able to take advantage of that would be potentially useful.
Yeah, and it depends on your tolerance, right? What you're willing to withhold. But for this, yeah, it's just right through. But we could do right back if if it's scratch and you don't care about potentially losing data or something like that. There's some options.
Okay, I think that's all we've got time for.
Great, thank you guys.
Thank you.
Yeah, thank you.